Now to start the semifinals, let's talk about the differentials, which is the first topic in these semifinals. And you've already done this without you noticing, and you might be remembering when I told you about the derivatives expressed in terms of Leibniz notation. So you can read from here that this is the result of having the derivative expressed in terms of Leibniz notation. It's just that we're separating dy with dx, but the idea is that it's just the same y prime. So if you have, for an example, let's take a very simple example. Let's say we have y equals 5x squared, and then let's add some 3x and then 4. Okay, so if I want to take the derivative using Lagrange notation, I have y prime that is equal to 10x and then plus 3, and that's it for the derivative. The derivative is 10x plus 3. Now we can also express this in terms of Leibniz notation by simply taking dy over dx instead of using y prime, because remember, y prime is simply equal to dy over dx, and in this case I will have the same answer. That's 10x and then plus 3. Okay, now to express this 10x plus 3 in terms of its differential form, you multiply both sides with dx so that dy and dx get separated. So it's like you leave dy alone at one side of the equation. So we have dy that is equal to 10x plus 3, and then we have here dx. That's simply how our differential works. And it's fairly easy if you would just take the derivative of y as if it turns out to be dy. I mean 1 times dy, and then this x, it becomes dx, meaning 1 times dx. So any derivative that you do, once you have x, you attach dx, and then for every y you have to attach something like dy. So this is true for all variables. Let's say you have another independent or dependent variables, let's say r, as long as it's not constant. So if you want to take the derivative of r, we have 1 times dr. It's something like that. If you have, let's say, r squared, then it becomes 2r and then times dr. So actually this looks something like your time rates. It's just that in time rates you have something like over dt. But the thing is, it's just the same. You just attach the differentiating variable, may it be dependent or independent, and then you're done with the differential. So let's try doing some from here. And the notation is given like this: dy is equal to the derivative times dx. Now let's try doing this one. Y equals sine x plus x squared. So we know that the derivative of sine x is cosine of x. And then we have 2x for our derivative of x squared. So in this case, you just have to add dx. Okay? And you have to add dy here, which is equivalent to the derivative of y. So that's it for our answer. You can see it from here that it's a very simple one. Now let's try doing this one. The t is equal to 3s squared plus s plus 2s squared cubed. So in any case, the problem doesn't tell you about the letters not being constant, so you'd assume that these letters can either be dependent or independent variable. So with this, the derivative of t is something like 1 times dt, so that's dt. This is equal to the derivative of 3s is squared is 6s, and then you can already attach ds, and then plus we have power rule, so that's 3, and then s plus 2s squared, and then minus 1, so that's squared, and then we have 1 plus 4s, and then you attach ds from here, okay, because you differentiated s. And then you can also factor this ds, so you will be able to get this equation from at the left. Okay, so that's it for number 2. Now let me just erase it so that it doesn't get too crowded. Now how about this h equals u plus pv? Now this is actually an equation of the enthalpy, and it really looks familiar to you if it is. So h is equal to u plus pv, but we don't need to understand the terms right here. It doesn't matter. We just need to identify the independent variables. In this case, since the problem doesn't tell any constant, so we would assume that all of these are independent variables or dependent variables. So what we have is dH, and then the derivative of u is 1 times du, so that's du. And then PV, so we have PV, they are different, so we just have to apply something like product rule. So we have plus P, and then the derivative of V is 1 times dV, so that's dV. And then we have plus V, and then the derivative of P is 1 times dP, so that's dP. Okay, that's why the answer here is something like this. Okay, so now let's proceed with number 4. It says here that the Gibbs free energy, or G, so in the equation it's here G, at constant entropy. So constant entropy, it says here that the entropy is S. So we need to find the differential of this equation. G is equal to H minus Ts. Now, if we would take the derivative of G being the dependent variable, so we have 1 times dG, so that's dG is equal to H, so that's dH minus T ds, so that should be something like minus T ds, and then because it's a product rule, so plus S dt. Now we can go back to the problem, and it says here that this is in constant entropy. So this is the general form without us considering any letter that is a constant. So in this case, it's constant entropy S. So if the entropy is constant, we know that this Ts should be equal to 0, because typically that doesn't change. So we know for a fact that the answer that was left is this dG is equal to dH minus S dt. That's why this is our final answer. Okay. Now we move on to the last problem, and it says here that if the hydrostatic pressure of a closed container is given by P is equal to rho GH. So this is actually the hydrostatic pressure equation, wherein the density is 980 kilograms per cubic meter of oil. So we need to calculate the maximum possible error of the differential pressure for a differential error in height of 0.003. So for a height of 2 meters, what is the percent error? Okay, so now we go back with the problem, and the first question is, what could be the differential pressure given that we have a differential error of 0.003. So if we're talking about the differential pressure, we know that we need to take the derivative of this expression so that we get the derivative of the pressure. So in this case, if I have P is equal to rho GH, I can just take the derivative of this. So the total differential would be something like D of P is equal to rho G and then dH. Now, you might be thinking, why didn't I just apply product rule in this case? Because based on our previous problem, we didn't have any constant stated here, so I used product rule. But knowing that it's density and G is the acceleration due to gravity, I know that for a fact that that's a constant based on our based on the basic knowledge that we know in physics. The density in this problem is not stated as if it's a constant, but you won't find any given or any other additional information in this problem wherein it says that the density is a variable. So in this case, it is safest to assume that this density is constant rather than it's an independent variable. So in either way, if I would be choosing that this is an independent variable, this density, then I won't be able to get an answer. So when solving, and then you just ended up being on a dead end because there is something like a variable that needs to be stated, or let's say a variable wherein it has to be given with another value, then most probably that variable should have been a constant that you might have forgotten during your computation. And usually in chemistry, we treat density as if it's constant, but in more chemical engineering or higher engineering subjects, we know that density is actually dependent on the temperature. So, but in this case, we'll just consider that it's constant. Anyway, so we're done with the derivative. So if you're differentiating something and then you know that that's a constant, you can just copy it and then differentiate the rest. I could have done the same thing for this. Knowing that entropy is a constant, I could just differentiated T and then just copy S. That's why if I would be differentiating this, that's dG is equal to 8 dH, And then I can just copy this s because that's a constant, and then the derivative of t would be dt. That's why I will be having the same answer in this case. I just performed the other one a while ago because I wanted to show you that you can actually cancel cancel expressions from the general expression that can be obtained from the equation itself. But in this case, since if I would be using the total differential as if nothing is constant here, this is quite a long solution because we have actually three different variables multiplied. So the best thing that I have to do here is to treat those rho g being the constant and then differentiate h, because that's it. It's the easiest method. Okay, so dp is equal to rho gh. So I just have to substitute all of these values. So we have 980, that's in kilogram per cubic meter. So we can just write the unit, but as long as you're consistent with the MKS, so I know you're quite familiar with this, but if not, then MKS is in meter, and then kilogram, and then second. So as long as your units in length, mass, and then time are on these respective units, then you'll be able to obtain all answers in MKS as well. So with this, the units are actually MKS, so I don't have to write it anymore because I'll be able to get the same. And then for our G, that's 9.81 meters per second squared, so that's also in MKS. And then DH. Now for the DH, it says here that DH can be equated into something like H sub 2 minus H sub 1. This is the rough estimate of any change in our height. But we have to remember that this, the DH, or we could say that it's approximately delta H, we should note that that's the infinitesimal change. So if you're having problems regarding this H2 minus H1, you can just actually subtract the two values. But the main point here is that if you have a lot of values given, let's say from H1 to H5, being, let's say you have H1, H2, H3, and if we're asked for DH, the best method to determine that is to take the most or the least difference that you'll be able to get, because that's actually the meaning of this DH. It's actually the least difference. So it's not always something like this, but you can roughly give an estimate to this. But as long as it's infinitesimal change we're talking about this, it's actually very, very small. Okay, so anyway, so in this case, the differential error in height is 0.003 m, so that's our DH in this case. So we have 0.003 meters. So you'll be able to get an answer of 0.8414 Pascal. So, I'm sorry. So your answer would be 28.8414, and then that's in pascals. Okay, so this is the answer for the first question. That's the differential pressure, and this is what you've obtained. So the truth about this DH is that the problem shall give you the differential change, because if it's not, then you can always take this assumption of the difference between two values. But remember, as long as we're talking about the differential term, we need to make sure that it is always the least of the values that are available. That's why most of the time the problems do not give two values wherein you have to like subtract them, because that's just the rough estimate of that. So I hope I'm making myself clear to that. This DH is the infinitesimal change, that is assuming that you really have very small value of your change. But in this case, since it's given that that's the difference, then that's 0.003 meters. And usually it's the least that you'll be able to get. Then again, if you're given with H1 and then a lot of other values, and then if you're asked to find the differential in height, then you pick the least. But of course, if the problem states that at that change, this specific change is this value, then you'll be selecting that. And you'll understand more of those when you encounter such kind of problem. But we're not done yet. It says here that for a height of 2 meters, what is the percent error? So what we have to do here is to find the pressure when the height is 2 meters. So in this case, let's find P. P is equal to rho GH, and if H is equal to 2, then we have P is equal to 980 times 9.81 and then times 2. So in this case, this gives us the value of pressure, which is 19,227.6 Pascal. And to be able to obtain the percent error, we could just write the percent error is equal to this value, which is TP over P times 100%. That's it for the percent error. So we have 28. Sorry, I just used the same page as your handout or module. Anyway, so that's 19,227.6 times 100%. So you'll be able to obtain the answer for this, which is actually equal to 0.15%. So this is equal to 0.15%. So that's it for our next question. That's the percent error. Now, one of the uses of differential calculus is to approximate values, especially when you're looking for the zero of a function. Now, let's go back to understanding how the zero of function works. If you have a Cartesian coordinate system, so let's have one here. Let's say this is the Cartesian coordinate system, and then there's a graph of a function. Let's say this is the graph of that certain function. Okay, so this is the graph, and then if you're asked to find the zero of this function, let's say this one is f of x, you would note that this has 5 zeros of a function, meaning any value of x that would make the equation equal to 0. So I have actually 5. Let's name them, let's say A, this one is B, and then C, D, E. So these 5 zeros of a function can be obtained using this approximation method formulated by Newton. And there's also this explanation. This method uses tangent lines to approximate graph of a function near its x-intercepts. So the x-intercepts are this value. So if a function is continuous on the interval AB, such that we have f of a and f of b different signs, then there exists at least one zero on the interval AB. So it just only means that, why is it important that they have actually different signs for this? Because if we know for a fact that if we select this interval, for example, these two intervals, let's say this one is A and this one is B. So we know for a fact that if we have f of B, we know that this is actually positive because it is at the quadrant 1. And basically, if we have to take f of A, we know that this is actually negative because it's on the 4th quadrant. Now, since they have two different signs, then according to that theorem, it says here that we should have a 0 at that of the function between the interval, and that makes perfect sense in this case. So that's also true if you would be taking the interval between these 2 points. Not necessarily the global maximum or minimum, but just between the intervals we're in, there's a change in sign. Because if you would look at the graph, you would see that the change in sign actually gives us the fact that between that interval, we will be able to get a 0 of a function. But anyway, you don't have to test it as always. It's just that it just proves that theorem. Anyway, so let's move on with this equation, and let's copy this equation first. Now it says here that this is that formula. So using this formula, we have x of n plus 1 is equal to x of n minus f of x of n is over f prime of x of n. Now I want to explain something about this formula first. X of n plus 1 means that this is the 0 of the function that you'll be able to get from a certain x of n. Now let's have x of n, right, something like here, near D. So we have x of n. Okay, so what this equation would do is something like generate a tangent line at this point, and then it will give you the answer to this x of n. Now, as we move towards this x of n, this would actually give you this kind of values, and then you further do that, and then this would come closer to this value, which is at letter D. Now, x of n is actually given in the problem. let's say for example you start with this kind of value, so you just have to find the number of, sometimes it's the number of times you have to like do this in order to get the 0, or what could be the possible value for your 0, which is at letter D. So in this case, it just makes perfect sense that x sub n should be given, and then the answer that you'll be able to get when asked to find the 0 of the function should be this letter D, because this is something like what the calculators do. You start with this x sub n, and sometimes we call it this memory of the calculator, and then you start with the iteration process. Now, iteration is a process wherein you use this formula several times. That's why if you use this formula several times, I've already told you about this, so it will just come close to that certain value. So until it gets to a point wherein the answer is actually 0. So it doesn't make perfect sense when the formula will just trace this graph and then it goes to Z, because that's actually the farthest answer for, I mean, it's a farther answer than this D, or it could have been E, but it has to trace the graph, so it should something like give the value of our D in this case, I mean of our letter D in this case. So knowing that we have x sub n, so your answer would be x sub n plus 1, and then you just have to substitute this x sub n to the original equation and then divide that with the derivative. So let's start first with the easy one, which is because in this module it's actually quite complicated. So let's start with a simple one. If I have, for example, an equation which is y is equal to, let's say, x cubed plus 2x squared minus 6, okay, and I want to take the 0 of this function. Actually, the easiest way to do this, to find the 0 of the function, is just equate this to 0 and then x cubed plus 2x squared minus 6, and then you press shift solve. Actually, that's the answer already. X is equal to blank, and then if there are 2 or 3, then you just have to get the value. So you'll be able to get, because it's cubed, then that could probably be 3, but as you can see, the sign changes just 1. So probably we only have 2 of them. Anyway, the idea is something like this. That's just the simplest way of finding the 0 of the function. And I'm not I'm not actually prohibiting you to use your calculator, so that's the easiest one. But for the sake of mathematics, let's solve for this using this kind of formula. And it says here that we need to find the derivative first. So let's find the 0. So let's say the instruction says that we need to find the 0. So find the 0 closest to, let's say, 5. I don't know if there is a 0 that is close to 5, but then this iteration would that would be done consecutively, and then you'd be able to at least come close to a 0. Okay, now from this problem, we know that x sub n is equal to 5. So for the first one, we need to find this f of x sub n. So f of x sub n is simply substituting 5 from our equation. So in this case, that's actually equal to 5 cubed plus 2 times 5 squared minus 6. So f of 5 is equal to 169. Okay. And going back to this equation, we can see right from here that we need to find the derivative and then substitute 5 to that derivative. So in this case, I'll be taking the derivative. So I have y prime is equal to 3x squared plus 4x. And then I need to substitute 5 from this equation. So we have f prime of 5, that is equal to 3 times 5 squared plus 4 times 5. And in this way, I have f prime of 5 equal to 95. Okay, so from this equation, I know that I already obtained the necessary values. Now I can now substitute from this equation. So that is x of n plus 1, that is equal to 5 minus, we have f of 5, that's 169, and then divided by 95. So the answer from here is 5 minus 169 over 95. So that is equal to 306.95. I'll be writing this in fraction so that I can get the most exact answer. But in this case, that's around 3.2211. So as you can see here, starting from 5, our answer became 3.2211. And basically, the trend would have something like it goes to the left side of the graph. So for example, if I started with 5, so it's something like moves from here. So I would have to expect that the value is less than 5 in this case, because that's the first trend that this graph did, or equation did. Now let's proceed again with using this. Now we have x of n plus 1 being our 3.2211. So you can just write x sub 0 when you start to solve for this, so that in this case you would be able to get x sub 1 since that's 0 plus 1, because it's a lot easier for us to remember. So in this case, let's have x sub 1 meaning equal to 306 over 95. In this case, I started with x sub 0 meaning 5, and then after the first process of finding using approximation, the answer is 306 over 95. And then you would have to do that again so that you would be able to get the same answer. Then you stop. So you stop, and then you only stop when your x sub 1 or your x sub n is equal to x sub n plus 1. So you stop only when x sub n is equal to x sub n plus 1. So it doesn't really matter if you stopped after 5 or 6 or 7 or any n number of interpolations. It's just that once you started with a certain number, you have to end up with the same number, and in that way, that's the 0 of that function. So let's proceed again, because 5 is not equal to 3.2211. So we'll be using this. Let's have 306 over 95 again. So we have x sub 2, that is equal to 306 over 95. I'll just be using the same equation, because that is your x sub 1 now, and then minus f of x sub 1. So we have minus, so we go back to the equation, then substitute 306 over 95 from this. So we have f of 306 over 95, that is equal to 48.16936. And then if you want to take f prime of 306 over 95, I just have the same derivative. You just have to substitute it from this equation. So that's 306 over 95, and then square that, and then you multiply 3. So the answer is 44.00975. So in this case, the answer from x sub 2 is 48.16936 over 44.00975. So with this, x sub 2 is equal to 2.126537. Okay, so to evaluate this, 3.2211 is not equal to 2.126537. So you don't evaluate as if it's 2.1265 is not equal to 5. That's your original. You compare with the one you used and the latest. So it's like this x sub n and then n plus 1. So in this case, 2.12 is not equal to 3.22. You just have to do it again, so x sub 3. You do the same process, and then you should be able to obtain your answer in this problem. So doing x sub 3, you'll be able to get, that's 1.5529 for x sub 3, and then you do it again for x sub 4. That's just the same procedure, and you will be able to obtain a value of 1.361936, and then do it for x sub 5. So this process of repeating is what we call the iteration process. And as you can see, from x sub 4 to x sub 5, they're actually very close to each other now. So we should be able to get the same answer at the next, probably. So that's 1.34025 for x sub 6, and for x sub 7, I think this is the final answer. So 1.34025. Okay, so this is our 0. And you can check your root by using your calculator. You can just try shift solving. So you'll be able to get the same answer using shift solve. Now I have your calculator. Let's try using our calculator to check on this. And it is very easy for a calculator to find this. If you have to find the closest or the zero closest to 5, you just have to type the equation. So that's x cubed. We have x. So if you need to find the 0, we just need to set this equal to 0, and then we press shift solve, and then it says here to solve for x. In the problem, it says here that we need to find the 0 closest to 5. So in this case, let's press 5, because that would be the starting reference of our iteration process. You press equals, and then that's it. That's 1.34025. So the background of this calculator, based on the system or the program of this calculator, we're actually doing this, the one that we did. It started with this one, interpolated, and then it checked L minus R. The L minus R is something like this, 5 minus 3.221, and then the calculator seemed to have a value that is not equal to 0. So in that case, it actually proceed with the next interpolation. So in the second interpolation, it obtains something like 2.1265, and then it says L minus R again, so it subtracted 2.1265 from this 3.211, and it didn't give an answer that is equal to 0. So with that, it continued interpolating, and then after this, probably it stopped at 6th or 7th interpolation, and L minus R, if you would see it from here, from our equation, x sub 6 minus x sub 7 is actually equal to 0. So that's what really happens on a calculator. That's the background process that's happening. We just did that manually. Okay, and then that's it for for the easiest. That's a very easy problem when you have a calculator. Find the 0 closest to 5. Now, what if the question is find the approximate value of 0? Value of the 0, or just the approximate value after, let's say, after 3 iterations. Okay, so if this is the question, then your answer should be something like after 3 iterations, so that should be x sub 4 if you started with x sub 0. So after 3 x sub 3, sorry. So if you did 3 iterations, then you should be able to get x sub 3, and in this case, the answer should be 1.5529. So after 3 iterations, the approximate 0 of the function is 1.5529, and as you can see here, it's not the exact answer because the exact answer is obtained at x sub 6, but the problem asks for this, so this should be your reported answer. Okay, and to do that in your calculator, because your calculator will just give you an answer that is actually the last, meaning that's the exact answer. So for the third interpolation, let's do this. Let's write this general formula using our calculator. So I have x, that's x sub n, minus, we have here f of x sub n. So in that case, that's the actually our equation, original function. So let's just write the function. X cubed, we'll be using the same. So x cubed plus 2x squared, then minus 6. And it says here that I need to take the derivative of this. So you can just use this derivative. We have 3x squared plus 4x, or you can use this function. So I'll be using this one because I think that's easier for me. But you can just write 3x squared plus 4x at the denominator, but I'll be using this. So once you use this derivative function, you make sure that the one that you'll be writing inside this derivative function is the original equation, because this would actually have to differentiate it first before it substitute values. So we have x cubed plus 2x, because this one is the more general approach, because I'm actually writing the general equation itself. Okay, so in this case, what is x? You just have to write x. Okay, so x is the value of your x. Okay, so now let's try if you would be able to get the same answer. Let's start with press calc and then press 5. In this case, I will start with 5, meaning our x sub 0. So this calculator should give me an answer that is 3.2211. Okay, that's it, 306/95. Okay, that's the first iteration. And then how do we do the second? Just press calc again, and then you press answer. That means that this x is now 306 over 95. You can just write 306 over 95 and then press that manually, but for the sake of this very simple and then very for lazy people solution, then I'll just use answer. That's so that I would have to like because if the answer is something like it has a lot of decimal points, you wouldn't want to write that whole decimal point manually. So the best one is just press answer, and then it should give us the value that it's around 2.126537. Okay, that's it for the second. Then for the third one, press calc again and then answer again. So it should give you the third, which is 1.5529. Then you press calc again and then answer. It should give you the fourth, so that's 1.36. Then for the fifth, so 1.34, and then for the sixth, this one, and then for the seventh, it should be almost the same answer. Now, if your calculator is having problems having that certain timeout, so instead of writing ands, you could just try to minimize the decimal point, because the derivative is actually having problems with that. So there you have it. But if you do have the derivative and this is a simple derivative, 3x squared plus 4x, instead of using this 1 d of dx, you can just write this 3x squared plus 4x. In that way, this calculator wouldn't have to time out for the computation. But I use this one because that's a general form based on this formula. And what if you're finding it really difficult to differentiate? So you can just use this idea. Okay, so that's us using the mathematical method of iteration in a human way, proving that the calculator is again correct and faster than us.